Hi guys, another quick video for you. This time it's a so-called electronic transformer, as people in my country like to call it. It's essentially a device that is used most often not most often, is used for halogen lighting. Normally old school way for low voltage halogen lighting, you'll have a large iron core transformer like that bastard right there, as you can see. It's a large stuff, weighs probably like 10 pounds or so, and it gets replaced by this circuit, which is right here. This circuit uses two transformers, one small transformer wound on a ferrite ring, which is right there, and another transformer, a power transformer, which is right there. A power transformer I scavenged from a type AT power supply for an old computer. Doesn't have to be real powerful stuff. 230 volt job that was, and that's fine. Cross section of this core. Some people just like to show you essentially a circuit, how it works, how well it works, and won't share anything with you. I share everything that you need in order to replicate the circuit yourself. Transistors I used are MGE 13009s. Small transformer as a core from a CFL's ballast. You can see a ballast, you can see a core right there, green stuff. And another ballast here just to show you. Another ballast, yellow core. They are old ferrite cores. Use a small ferrite core there. Follow the turns, follow the phasing, that's what dots mean. 3 turns here in the bases, 8 turns here in the feedback winding. I used 100 turns here, but you can use 90, although I like using 100. And for a 12 volt output, effectively on a 40 watt load, and I'll explain in a minute what this is, you need probably like, well, in my case that's 8 turns. Oh wait, 6 turns, yeah. You can actually wind a little bit more, like 10 turns, give it some active load, powerful resistor, scope across it, cause the output waveform is AC and it's a square wave. So you have to measure peak to peak voltage, then measure peak voltage, and that's effective RMS value of that waveform. But anyway, as you can see, the schematic is really simple. It's a half bridge, self-oscillating, uses very few parts. As I mentioned, I told you all the windings. Cross section of this transformer in my case is 70 square millimeters. That's necessary. You can't just go and make such a transformer for the circuit on a core which is very tiny, like this one. You can't. You can see how small that is. You need a 70 square millimeters or more. The transformers in this kind of power supplies, ATX types, are pretty much all the same. Just pick a low power job and you'll be fine. That was extracted from a 230 watt AT power supplies. Yeah, so let's show you some waveforms. You can see clips connected and a scoping right across it. And what this is, it's actually my neighbor. He's a beekeeper, and this thing is essentially a hot knife for cutting the I just don't know how to call it. You will say an annotation what's that thing called, like, you can see there, 12 volt, 40 watts. And he brought me that transformer, which is 36 volts transformer, and asked me, can I power this from that? I told, well, yeah. I thought initially that I can use a phase-fired controller on the secondary side to power it. It didn't end up quite well. Then I got into problems where I needed a very small conduction angle with a triac circuit, that I can just make this scene start up reliably. And if the mains voltage will sag just a little bit, like 5 volts sag, it will just go off and won't trigger at all. Anyway, enough babble, let's show you some waveforms, shall we? Running through a balance just for the safety sake. Right now I actually developed the circuit very well, so I can run it straight to the mains voltage. And the waveform looks like this. You can see quite a neat looking square wave. By the way, their scope is set to 5 volts a division for vertical and 5 microseconds for the sweep. So the frequency is about little more than 40 kilohertz, I believe, or 30, whatever. And there are, you can see, 5 volts peak to peak, thus peak voltage is 5 divisions peak to peak, I'm sorry, thus 2.5 divisions peak. So it's 5 divisions. Yeah, 5 volts a division by 2.5 divisions, so that's 12.5 volts, which is perfectly fine. And the thing gets hot, because it's a heater. You may see that wax or whatever they used to is molten here. See? In fact, I can't really show you that it's hot, but believe me, it's hot. You can see that it's molten, right? You can see me sweeping my finger across it, and you can see a wax residue on my finger. So the thing is hot, this thing is not. Awesome. So the next step forward will be, in order to make it usable for the end user, to make this a board which I'm gonna put into an enclosure. Gonna probably put some sort of heatsink on it, like a little L bracket that's gonna go like to the transistors and over like that, and into the enclosure. An end user can put a mains here on this screw terminal and load here. Right now I'm running 5-watt load just for the sake of it, in order to demonstrate it. Gonna plug it in. As you can see, it lights up. Plug it in again. Bulb is nice and bright. 12 volts it is. You can see the board up close. And yeah, I forgot to mention that this thing afraid short circuits on the output. This way, the way it's set up, this winding, as you can see, is in series with the primary of this power transformer. So that's so-called current feedback. That's, by the way, a so-called Jensen oscillator with a current feedback in this case. Current proportional drive or something like that it's called. It has an advantage of efficient switching, and when it's designed for a given load, it operates quite efficiently and the switches does not heat up much at all. But if you short the output or overload it, the transistor is just gonna blow up in an instant. But if you gonna put some nice load on it, you'll be just fine. And yeah, this thing won't start up without any load, because again, current feedback, proportional current drive, so it needs some load, some minimum load in order to start up and work properly. 5 watts seems to be enough load for it, and it starts up and works reliably. Nothing heats up. By the way, do not touch the collectors of the transistors if the thing is plugged in, unless you are running an unless you are using an isolation transformer, because collectors, as you can see, one collector sits here on the positive rail, which is connected through a rectifier. Let me show you actually. I made a full schematic. Of course it's connected to rectifiers, that's why plus is there and minus is there. The full schematic is here. By the way, I counted the correct number of turns, and that's 8 turns on the primary, on the secondary. Yeah. Well, after thinking for a bit, I actually went and put a heatsink on it. Heatsink on it, as you can see, is really ridiculous heatsink, but to be honest, it doesn't really need it. I just put a heatsink there to add the reliability there. I have a choice of running without heatsink, but I have practically no space limitations, so why not to put a heatsink there? And since it's insulated, you can touch it, and it's warm, like, you know how warm, like a nice furry cat warm. Pleasant temperature. You can literally hold your fingers there and relax. Really pleasant, like, again, like 40 degrees. Perfectly fine. This is hard though. You can see it's shiny because it's melted that stuff on it. You can see, damn, it's hot actually. Quite hot. I didn't expect it to be that hot. So that paraffin that they used as a preservative before usage for transportation has a quite high melting point actually. I thought it will melt at 50 degrees or so. Oh, yeah, 50 degrees is hot to touch, so that makes perfect sense. Anyway, so this time for real. Actually, it's such nice stuff. I don't want to really give it up, but I can make another one if I want to. I just need to find a transformer, or I can make a toroid actually. Make it on a toroid. I do have a couple of toroids, but they are not that good. Not that big of a cross section. I don't wanna give you up, I don't wanna let you down. Oh well, I'm gonna put it into an enclosure, and that will be it. Thanks for watching, see ya.